So welcome everyone. Now that we're recording, just a couple of quick reminders how this whole thing is going to work, and we'll be on our way with the talk. So we're in for 1 hour talk and up to 30 minutes of discussion. The talk is being recorded because the recording was started. And we ask that during the talk, you keep your mics off. Unless you're the speaker, then please keep your mic on, and cameras on. If you want to ask a question, please just unmute your microphone and ask the question. And I think that's pretty much it. So with no further delay, I'm going to introduce our speaker today, who is Benno van den Berg from the University of Amsterdam, and he will speak about uniform cofibrations in simplicial sets. So, Benno, your mic is on, and I'll...
Okay. I hope everyone can hear me. So thanks, first of all, for the opportunity to give this talk. So first of all, I should say that this is joint work together with Eric Faber. Maybe I should apologize to the people who have been at the hot meeting in Pittsburgh. They might have heard this talk before. But I've thrown in some additional details, so I hope it's still worthwhile for them as well. Before I start, I want to take 1 minute just to well, express at least my some shock and sadness that Erik Palmgren has unexpectedly died. Actually, I was in Stockholm 2 weeks ago, and I didn't meet him then because he was ill. I mean, what I heard was a bit worrying, but well, I think this was still very unexpected for anyone. Basically, I've known Erik since I was a master's student, at least from his writings. I mean, I've been the papers that he wrote together with my former supervisor, Erik Palmgren, are the first scientific papers I read on W-types, predicative toposes, algebraic set theory, and later also on constructive non-standard analysis. And always when there was a paper written by him, it was a sort of important touchstone for me. Also, my first scientific visit abroad was to Erik when he was still in Uppsala. And I just remember him as a very sort of kind and encouraging person who would always sort of have his own opinions, but which were always I would always sort of respect very much. Maybe in the context of homotopy type theory, it's maybe good also to remember that he actually organized the first, I think what we would now say, meeting on homotopy type theory in Uppsala in 2006. I mean, it wasn't called homotopy type theory then. So I think in that sense, he has also made an important contribution to our subject. Maybe he was more patient with setoids than many of us. I mean, but always also there, he was always sort of worth listening to, and I think it is a great loss for many who are listening, both scientifically and personally. Okay. Having said that, so what I want to talk about today is actually goes back also to the early days of homotopy type theory. So the moment it became sort of fashionable and basically was when Voevodsky made his contributions to the subject. And the key was really, one of the key ideas was his idea of interpreting univalent type theory in simplicial sets. And as we probably all know, I mean, the idea is that the types in type theory are to be interpreted as Kahn complexes, dependent types as Kahn fibrations, and in this way you get a model of sort of univalent type theory. So he heavily exploits the existence of a Kahn-equivalent model structure on simplicial sets. And if you delve into the proof, you will quickly discover that there are some aspects which actually make it non-constructive. So if you say, if you want to fix a meta theory, it probably should be something like Z of C plus a few inaccessibles, depending on how many universes you want to interpret. And one question people quickly ask themselves is this also provable in a constructive meta theory? And just to make fix things, I'll say that by constructive meta theory, I mean axial set theory, CZF, let's say, plus a few inaccessibles. So yeah, I mean, of course, one can try to do this in type theory as well, but that is probably going to be rather difficult unless you work in something like extensional type theory. So anyway, don't really want to go there. Let's say, just to fix things, axials constructive set theory CZF. Or let's say the internal language of a topos, if that's more familiar to you. Well, so I think very quickly, I mean, people discovered, well, I mean, already quite a while ago, maybe I should say, is that one of the key results on which this relies is the fact that you want to interpret function types, or maybe more generally pi types. And there is this result which says that if A and B are Kahn complexes, then A to the power B is also a Kahn complex. However, this result is not provable constructively. So, as was shown by Bayes and Kahn and Parman. So, this, of course, is an important problem because this is how we wanted to interpret how Voevodsky interprets the function spaces. And more generally, we want to interpret pi types as sort of, so also the more general result, which says that if you have two Kahn fibrations, then you can take pi of one along the other and should again be a Kahn fibration. So also that is not constructively provable. So in response, people have, I mean, especially people following Cofibrations and his collaborators, and also people elsewhere, have basically switched to cubical sets, and they've decided to strengthen the notion of fibration by adding what are now, I think, now called uniformity conditions. So what I want to do today is I want to stick with my simplicial sets. So I'm just want to see how far we can get by just not switching our proof sheet category. Okay, so one possible approach would be that you just, I mean, as always, I mean, you can just take sort of the standard textbook definitions of Kahn fibrations and trivial Kahn fibrations, as you find them in most books on simplicial homotopy. So that would mean that you say, well, a Kahn fibration is something which has the right lifting property with respect to Horn inclusions, and trivial fibrations are those which have the right lifting property with respect to boundary inclusions, and one can sort of see how far one gets. So recently, Szumilo and Sattler proved that actually, even in a constructive meta theory, one can prove the existence of a model structure on simplicial sets. One thing which is a bit surprising about this is that if you do this, then not every object is going to be cofibred constructively. And that creates a few problems. For instance, so if you want to extend this result to obtain a model of type theory, you can try to do it. So it's done by Gambino, Sattler, Szumilo in some of the papers. But of course, the Bayes and Parman obstruction is still there, so you still have problems with interpreting pi types. So there's only a sort of a weak version of pi that you have. Some problems around stability. And also, I mean, if you want to sort of turn this into a genuine model of type theory, you need an appropriate coherence theorem. And the one that we seem to need is seems to be difficult to prove. So, so that's one possibility. Very interesting. But what I want to do is maybe also suggested by the work on cubical sets, try to see if we can define the notion of a uniform Kahn fibration. So just to be clear, what I mean by a uniform confibration, first of all, there is this sort of maybe almost philosophical distinction between structures and properties. So if you just read the textbook definition, and then you might think, well, then usually the existence of lifts against horns is treated as what we will now say a property. So these lifts should exist, but they're not part of the sort of the structure of a confibration. And I think it is, I mean, people who want to do things constructively, I think all agree that that's probably not how you want to do it. Also in the Gambino-Henri approach from the previous slide, they also say, well, we really think of it as a structure. So what we really want is that if you give me a square with a horn on the left and a fibration on the right, then there should be, the fibrations should come with an explicit choice of such a filler. And that is sort of part of the structure of being a fibration. So that's indeed also the approach that we will follow. And then the question arises whether you, on these pillars, you want to have certain compatibility, or what people now usually call uniformity conditions. So should all these pillars just be completely unrelated, or should the basic, I mean, do you want these choices, to make these choices in some sort of compatible way? And so we think that will be a good idea. So that is basically the approach that we want to take. So basically what we want to do is that we want to define the notion of uniform confibration in simplicial sets, such that we can prove constructively this result, which says that they are closed in a pi, or maybe closed under just taking exponentials. In a constructive matter theory. So somehow the idea is that these uniformity conditions, they contain the extra information that we really need to prove this result in a constructive matter theory. So they give us a bit more sort of structure to work with. The idea is that these uniform confibrations should have the right lifting property with respect to horn inclusions. So they should be confibrations in the usual sense, even in a constructive matter theory. But if you want to prove that, if you give me a map and it has the right lifting property with respect to the horn inclusions, then somehow you need classical logic, or the axiom of choice, to prove that it actually can be equipped with the structure of a uniform confibration. But I mean, according to a classical mathematician, the definitions are in a sense equivalent for that reason. But the last point is probably difficult for the constructivist. Okay. So that's the idea. I mean, we want way more than just this, but this is at least what I think I can confidently claim that we can do. There's one possible objection right away, and that is the fact that this has already been done. So why am I claiming that I can do it as well? Well, the problem is that, yeah, so there's a paper by Gambino and Sattler where they also define the notion of uniform confibration, which has exactly these properties, and that's sort of the main point of their paper. But the key thing is that we can do something else, which was for them a problem, at least in the constructive matter theory. So they were unable to show constructively that the notion of a uniform confibration was local or locally representable. So what do I mean by that? Okay, so I mean, so here I'm borrowing some definitions from Mike Schulman. So first of, I mean, if I want to define this notion of a local notion of a uniform confibration, then maybe I should do it like this. So first of all, I define something like a structured notion of fibration. as follows. So on some category E. So if I have E is some category, and I have a mouse as well, and I write use this notation for the category of arrows, whose objects are arrows and whose morphisms are pullback squares between these arrows, then I can look at contravariant functors or contravariant presheaves if you want on this category, and call that the notion of fibred structure. So the idea is that basically to every morphism in E, I assign a set. The set of fibration structures on this map, which could be empty, in which case it is not a fibration. And this functoriality basically says that if I have a pullback square and I have a fibration structure on the right arrow, then I also have a fibration structure on the left arrow. And this is sort of, I can do this in a suitably functorial way.
The way of saying that.
There's a question which I can't hear.
Can anyone else hear me?
I can. Okay, I can hear you now. Sorry, I had to mute my phone. My microphone.
Is that a way of saying fibrant types kind of preserve judgmental equality or substitution?
Yeah, it's sort of a stability. I mean, there's a kind of stability under substitution. Yeah. Right. All right. So, so what do we mean by local? Okay, so it is. Okay, so it is basically some sort of sheaf condition, if you want. So I imagine that I have the following situation. I have a map F from Y to X in E. And, well, maybe I'll just illustrate it on the picture more than just trying to read this text. Okay, so suppose I have this arrow EF over here. And I imagine that whenever I pull back this map F to a map where the codomain is a representable, I have chosen a fibration structure on this arrow over here. And let's also assume that I make these choices in a suitably compatible way. So that means that if I pull back this arrow along another map, where again, this thing over here is again a representable, then of course I get another map. And that means that I've also chosen a fibration structure on this one. But what I want is that if I pull back my chosen fibration structure on the middle arrow, I get exactly the chosen structure that I had for the arrow on the left. So assume that I make a sort of compatible choice of fibration structures in this sense. Then I want it to be the case that there is a unique fibration structure on this map F, which pulls back to all my choices that I made earlier. So this definition makes sense in any presheaf category, and actually it makes sense in more general setting, in which case you have to reformulate it a bit, but I'm just only interested in the case of simplicial sets, in which case I can formulate it like that. You can also find this notion in Mike Schulman's paper on infinity one toposes and strict univalent universes. So in a sense, it's a kind of sheaf condition. And if you think about it, I mean, the usual notion of a confibration, so having the right lifting property against Horn inclusions, is local in this sense because, well, basically because the Horn inclusions have representable codomain. And that basically, I mean, if you think about it, that allows you to prove that this notion of structure, of fibration structure, is local in this sense. So this is something we want to have, in particular because it is what allows us to construct universes. I mean, if the notion of fibration would not be local in this sense, then at least I don't know how to construct universal fibrations in a presheaf category. I mean, we have this Hoffmann-Streicher construction, or universes à la Benno, which gives us a method for constructing universes in presheaf categories, but that really requires that the notion of fibration that we're working with is local in this sense. And if you're not able to prove this constructively, then we don't know how to construct, at least I don't know how to construct universes in a constructive meta theory in presheaf categories. So that's basically the one extra addition that I want to make to my wish list. So I want to have a notion of uniform confibration, which is closed in a pi. It's basically classically correct in the sense that if I have a confibration user sense, I can equip it with the structure of a uniform confibration. And the notion should be local in this sense. Okay, so basically, I mean, in the paper that I'm writing with Eric, and hopefully will finish before Christmas, we give one particular definition of such uniform confibration, which is maybe looks very difficult to motivate. So what I want to do instead in this talk is explain a definition, which is not really the one we use for proving anything, but is the one which I think is easiest to motivate. Basically, as a modification of things which have been done before. Especially, again, by Gambino and Sattler in their paper, where they actually follow what people are doing in cubical sets. So I suspect that what I'm going to say next will look very familiar to people who are familiar with the work on cubical sets. All right. So first I will explain the Gambino-Sattler approach, which is in some sense the cubical approach. So I want to do it in a particular way so that I can sort of explain our definition of a uniform confibration as a modification of that one. So first, I want to fix the notion of a cofibration. And so let's see. So normally speaking, a cofibration is just a monomorphism in simplicial sets. But now that we work constructively, we have to be a bit more careful. So the notion of cofibration that they work with, and actually it will also be the notion of cofibration that we work with, is where we basically make the additional assumption that if we look at level n, then we have the inclusion of the n simplices in B into the n simplices in A, and that monomorphism in sets should, if you want, should be complemented. So basically, so if you want, it should be decidable. If you give me an n simplex in A, it should be decidable whether it is actually in the image of M, and if so, you should be able to find the elements in B that it came from. So there is some sort of classically empty but constructively meaningful addition that you have to make to the notion of cofibration. Note, cofibrations are stable on the pullback. All right. Good. So how do we define a notion of a uniform trivial fibration? Okay. So basically what we want to say is there's something which has the right lifted property against all cofibrations. So that means that if you give me a square like this, and I have this map F here, which should be from a trivial fibration, and you give me a cofibration here, then it should have a figure. But what makes it uniform is the fact that we add a certain compatibility condition. So we could imagine the following situation, that we basically had two lifting problems of this shape. And so one is this form, and then here we have a pullback square. So this is a cofibration, this is a cofibration, and this is a pullback square. In that situation, we have two choices. So we have a lift over here because of M primed, and we have a lift over here because of M. And what we demand is that our chosen lifts satisfy the following compatibility condition. They should basically make this triangle, which they create, they should make that commute. So in that sense, it's a compatibility condition on the lifts. So this is something we do as well, but actually it is not enough for us, as we will see later. Okay. So this is uniform, this is their notion, the Gambino-Sattler, also if you want the cubical notion of a trivial fibration, uniform trivial fibration. And then the notion of a uniform confibration. in the sense of Gambino and Sattler. It's basically relatively easy to state now. Some places will say that the morphism F from Y to X is a uniform confibration if, well, a certain map is a uniform trivial fibration. So what we do here is, okay, so what is it? I is just the interval, or delta 1. And then we have the two endpoint inclusions into delta 1, the di's, delta i's. And then we can basically compute, write down this map, and that we basically say that the original map is a uniform confibration if this is a uniform trivial fibration. And note all of this is classically correct. I mean, this is all just another way of just defining an equivalent way classically to define the usual notion of confibration. It's actually really, yeah. As you can actually also find in the Gambino-Sattler paper where they mention this. All right. So, so I've written this out for people who enjoy this. Let's see. So what is it? What does it really say? It's essentially a path lifting property. It's just. So if you just ignore this stuff about the cofibrant sieves, it basically says, okay, if you give me a point in Y and a path in X where one of the endpoints is f of Y, then I can lift this path pi to a path tau. That's basically it. Plus that, okay, there is actually this condition on this cofibrant stuff. So basically what that amounts to is saying, well, I should even be able to solve this lifting problem even when on sort of cofibrant sieve. So let's say basically on a sub-complex, if you want, of delta n, I'm already told what the lift should be. And then I can choose my lifting and Y in such a way that it agrees with the sort of pre-specified lift on this cofibrant part S. Again, this should look very familiar, maybe not the notation, but the idea should look very familiar to people who've seen cubical sets, I hope. All right, if there are questions, then please ask. Okay, so this is the Gambino-Sattler approach. And the idea is that we're going to modify it. So let's just to state again, I mean, they prove that it is close to pi. They prove that this notion is classically correct. But the problem is that they have difficulties showing that it is local. And well, if you actually, the problem, you can actually already in some sense see the problem here and why the things work better in cubical sets. The fact that this delta n times the interval is not a representable is basically what causes, creates problems for them. And that's why things work nicely in cubical sets, because then this would actually be representable, and that's why you can prove constructively in cubical sets that this is a local notion of fibration, whereas this is quite difficult in simplicial sets. Okay, good. So what are we going to change? Oops. So we're going to make several modifications, maybe just, well, 3 in a way, modifications to this definition. The first thing is something to do with what in an early paper with Richard Garner we called Simplicial Moore paths. So this is idea that instead of, I mean, from topological spaces, so that instead of looking at paths of just length 1, you can look at paths of arbitrary length, and in that way you can compose paths in a way which is strictly associative and strictly unital by just looking at the path which is length 0. And well, we tried to do something similar in simplicial sets, and we came up with this strange functor m, which I will say a bit more about in a minute. But the idea is, in a way, quite simple. So this kind of notion of Moore paths basically equips every topological, I mean, basically makes every topological space yeah, sort of the object of objects of a category object inside topological spaces, and this M should do the same. So, so if you give me a simplicial set X, then this should become the object of objects of some internal category whose object of arrows is just M of X. And there should be maps like an identity arrow R, and then source and target or domain and codomain maps S and T, and then U is some sort of composition. And everything is natural in X. So R, S, T, and U are actually natural transformations. So in that sense, we equip every so every simplicial set becomes the object of objects of some simplicial category. And the n simplex in M of X we call Moore paths. So what is M of X? The way we actually going to do it in the paper is as follows. We're basically going to define it as a certain polynomial functor. So polynomial functors have already been mentioned several times on this in the seminar. So I hope people still remember what it means. To define it, we're first going to define a simplicial set T0. And the idea is that its n simplices are certain zigzags or traversals, as we will call them. So a traversal is basically a picture which looks like this, where so it's basically a zigzag of arrows between, and the edges in this zigzag are decorated with certain elements of sort of square bracket n. So they're natural numbers between 0 and n. Well, the first thing we should do is basically give this thing the structure of a simplicial set, which we can do. Actually, this was already done in the paper with Richard Garner. So the idea is something like if you look at a certain phase map, basically you remove all those edges which have that particular label. So this is DI, then you remove all the edges with label I, and then you sort of relabel the other the edges which have a bigger label. And if you act with a certain degeneracy S of I, then you sort of duplicate the arrows which have label I, and then you then you relabel everything else. And then there is some convention about if you sort of duplicate a label, or sort of an edge with label I, then you get an edge with label I+1 and an edge with label I. And if the edge points points towards the right, then the I+1 goes before the I, and if the edge points to the left, then the I goes before the I+1. Anyway, you can check that this is a simplicial set, and details can be found in the paper, the earlier one, not the one that we should still write. So this is actually an internal poset in simplicial sets, and it's not so difficult to see because we give it a sort of the final segment ordering. So, I mean, by that I mean just that something like this is a final segment of the other traversal that I wrote. So with this sort of ordering, it is actually a poset internally to simplicial sets. And so there's also an object C1, the object of arrows. So basically, in a sense, it's just a pair of traversals, one shorter than the other. Or you could say, and that's really the way we like to think about it, it's basically a traversal together with a choice of one of the vertices in the traversal. And then, anyways. So then you have if you think about it that way, then you have some sort of forgetful map from pointed traversals to traversals. You can take the polynomial functor associated to that, and that is M. And actually, if I studied the so from what I can, so actually this M is actually going to be an instance of something called a polynomial comonad that Richard Garner is probably going to talk about in the seminar in a few weeks. So so actually, I think I don't know exactly what he's going to say, but I'm pretty certain that this M is going to be an example of some of the phenomena that he's going to talk about. So that's quite nice. Actually, here was some conversations with Richard were actually very useful. So this is one way you could define it. This M, there's actually another way you could define it, which is also quite useful. And actually, that is the way it was done in the earlier paper. Okay, so this is maybe not the easiest picture in the world. The idea is this. So there is something to every such traversal, we can actually associate a certain simplicial set, where the vertices are going to be replaced by n simplices, and the edges are going to be replaced by n+1 simplices. And so for this n+1 simplex by 1, these two n simplices are going to be faces of that n+1 simplex. So basically, in this case, I'm going to have 5 n+1 simplices, which are going to be glued to stick together in a certain way. And there's a certain formula for how that should be done, which I've sort of, so it's basically going to be this colimit. The details are not too important, but it is important that there is some notion of some sort of geometric realization of such a traversal. And then another way of defining M of X is to say that its n simplices consist of a choice of such a traversal and a morphism of simplicial sets from this geometric realization to X. An interesting thing, and actually important, is that there is this very special traversal. And if you sort of compute its geometric realization, you will find that it is actually delta n times the interval. So there's this thing that delta n times the interval can be sort of obtained as some sort of the union of a number of n+1 simplices. It's a standard fact in the theory of simplicial sets. And for us, this is important because this actually is the geometric realization of a certain traversal. And just using that fact, you can also show that the normal path object, x to the power I, is actually going to be a sub-simplicial set of our M of X. Basically, it's just a sub-simplicial set where you only consider traversals which look like this. But basically, what we want to do is we want to consider general traversals. We just don't want to consider these very special traversals of this form. Okay. Good. So, this is an important ingredient, and probably actually the main ingredient for our definition of a uniform confibration. So let's go through the Gambino-Sattler thing again. So, but now in the way that we want to look at it. So we agree with our notion, as I said earlier, we agree with our notion of a cofibration. So again, it's something which is pointwise monomorphism and pointwise complemented monomorphism. So there's a decidability condition there. One thing we also observe is that these cofibrations are not just closed, just stable on the pullback, but they're also closed under composition. And we want that to be reflected in our notion of a uniform trivial fibration. So remember, a trivial fibration was something where you have this map on the right and a cofibration on the left, and you look at the square, and we basically want to have a uniform trivial fibration structure. Should be something where you basically specify an explicit lift for such a square, or an explicit filler for such a square. So there was this condition that we saw earlier, where, about this sort of pullback stability condition that we want to have as well, but that sort of reflects that these cofibrations are stable in the pullback. But we also want to have a condition which reflects the fact that these cofibrations are stable in the composition, closed in the composition. So what we can do is we can imagine the following situation, like in this picture over here. We have such a trivial fibration F on the right, and here we have two maps, which are two cofibrations. And then we have a square like this. So then, if you can try to find a map from A to Y, like this, in two different ways. First, you can say I compose M and N, and I get a cofibration from C to A, and then I can sort of find my chosen lift over here. Or you can also try to do it differently. You can first sort of think of this picture. So then, first you can say, well, I can also think of this F as opposite to this M, where I have this arrow basically from B to X, and then I find a lift from B to Y, which fills everything. And then, given this arrow from B to Y, I get a new square, and then I can use the fact that N is a cofibration to also find an arrow from A to Y. So I basically can either first compose the two cofibrations and find a lift, or I can find two lifts, just first using that N as a cofibration and then N as a cofibration. And basically what I want is that this, so then you create two arrows from A to Y, and what I want is that these two arrows are the same. So that's the extra sort of vertical compatibility condition that I want to have on my trivial fibrations or uniform trivial fibrations. Okay. That's the first modification. Then now the second modification. So what I want is, okay, so just remember that in Gambino and Sattler, in the cubical world, an arrow from F from Y to X is a uniform confibration if this particular map was a uniform trivial fibration. So here we see two path objects, here a path object and here a path object. And basically what we do is we replace them by our path object, the Moore path object M of Y. So what we have is that a map F from Y to X is a uniform confibration if and only if this map is a uniform, this map F from Y to X is a uniform confibration if this map is a uniform trivial fibration. And as you can unwind again, I mean, basically, again, it just says that if you have a point in Y and you have a Moore path, actually now we can always assume that this Y lives over the endpoint of this Moore path because they are suitably symmetric. These Moore paths are also sort of symmetric as well. Anyway, so if you have a point Y and you have a more path in X, whose endpoint is f of y, then you can lift it to a more path in Y. And again, we have this condition that if you already on some cofibrancy specify what the solution or what this lift should be, then you can find your lifts in a way which respects this. So this is again very similar with the cubical definition, only now we use more paths instead of just paths of. So basically, in a way, if you want, I mean, the main difference is that here we now have written a general traversal instead of, well, I mean, if we go back, we saw sort of these things, which are, from our point of view, basically very special traversals, namely the ones which came from pictures like this. So our idea is that basically you should look at more general traversals than just those. Good. Okay. So we've made two modifications, and then there is a final one which I want to make, which is crucial because still, I mean, the main thing is that I think it's more or less satisfied. I mean, this would already work. I think it would satisfy most of the properties, except for local character, which was the main motivation for just messing with their definition. So just to enforce locality, or to make sure that this is a local notion of fibred structure, I insist on the following condition, and which is the final modification that I want to make. Actually, I think I'm going to finish ahead of schedule, probably. Okay. Anyway, so if people have questions, then. So yeah, so basically, remember that these more paths they can be composed, and in a way which actually is strictly associative. In fact, the composition of these more paths is kind of easy because again, if I go back, I mean, the way you compose a more path like this with another more path is by just sticking them next to each other. So that is composition of more paths essentially. So imagine that I have the following situation. I have one big more path pi in X, and I can write it as the composition of two more paths, pi 0 and pi 1. So then again, I can do two things. Supposing that I have some y which lives over this thing X. I can either sort of lift immediately the composition, or I can lift in two steps. I can first lift pi 1 to some tau 1, and then lift pi 0 to some tau 0. And what the condition that I want to have, the final condition for my uniform configuration, is that this shouldn't matter whether I just compose in one go or I compose in sort of in two steps like this. So I think this is really what is needed to make the definition local. And I think, I mean, maybe I can sort of try to give some intuition why this is the case. If you basically, I mean, these more paths were basically given by these traversals and have a certain length. This condition that the lifts of this long more path are basically what it does is it forces the lift of the long more path to be completely determined by the lifts against the more paths of length 1, right? So every more path, or basically every traversal, maybe like this, can just be written as a composition of more paths of just length 1. And the lift against such a long more path is completely determined by the lifts against them, because they have to respect composition. They are completely determined by the lifts against more paths of length 1. But these more paths of length 1 are basically n plus 1 simplices. So in that sense, I mean, very roughly, basically, that's the reason why we would gain local character. So if you want, so in the sort of the Gambino-Sattler approach, basically they only sort of want to lift more paths which look like this thing. And basically, and this is some sort of union of n+1 simplices. And basically what we say is, well, your lift for this big union should be completely determined by the lifts for these individual n+1 simplices, which make up this big prism, basically. And by doing this, insisting on that, basically we force a notion of uniform configuration to be local. Okay. So that's, as I said, this is I think the best way to sort of maybe introduce our notion of uniform confirmation. This is a modification of the earlier definitions and work done on cubical sets. Basically, in our paper, we work with a definition which looks rather different, but of course is equivalent to this one. This doesn't seem to be, the definition I gave doesn't seem to be very good for proving things. At least we had trouble. Okay, so basically I want to sort of slowly want to ramp up. So basically, what have we done? So I claim that we have a notion of uniform configuration for which we can show that it's closed under pi. That it is classically correct. So even with adding all these sort of extra uniformity conditions that we've done, we can still show that classically, if you just have the right lifting property against Sworn inclusions, you can choose your fillers in a way which satisfies all these compatibility conditions. Yeah, sort of clear, I think that, for instance, our definition implies the Gambino-Sattler definition. Again, this is because they only look at very special traversals from our point of view. So our definition implies theirs, which implies the usual one. So that's fine. Of course, so we don't know. We can't sort of. What would be really useful is if we could actually separate these three notions. So if we could somehow prove by some sort of I don't know, prove that there are maps which constructively have one structure but cannot be equipped with some of the other structures. I haven't really thought about it too much, but it's probably not so easy. So the hope, of course, is that I mean, basically what I've just told you is that I have a model with pi type of type theory with pi types. Well, ignoring all the usual coherence issues, which I expect are not really a problem, but we haven't really thought about it so much. We have sort of done a few other things as well. So I think identity types are also possible, sigma types, well, natural numbers, and so on. I'm reasonably confident that we can. I mean, the things that, yeah, I'm reasonably confident that we have some sort of model structure, at least when we restrict to the Kahn complexes, at least also constructively. So the main thing which one should do is look at universes. I mean, we had this, okay, so now we can prove constructively that they exist. But we should prove that they are univalent, and we should prove that the universe is Kahn, and so on and so forth. So we have thought a bit about this. I mean, our hope is that we can basically follow the Sattler's approach in the paper on the equivalence extension property, but yeah, we still have to check this more carefully. Ideally, we would hope that we have some sort of notion of algebraic model structure on the entire category of simplicial sets as well, but we haven't done that. in one issue, which maybe I should, is that I mean, what we want, for instance, also is that this notion of uniform confibration is basically the right class in an algebraic weak factorization system. And I think we can prove this classically. So I expect that it is also true constructively, that also there are still things we need to sort out. Okay, so anyway, still lots of work to do. And so with that, I basically want to finish. And so thank you for your attention.
Oh, thank you very much. As is now the tradition, we will do silent applause. So we will clap, but we won't unmute the microphones. And, okay, and having done that, now we'll open the floor for discussion. So if you have questions, please unmute your microphone and ask the question. We have a good half an hour to go. So. No reason to be shy.
Okay, I'll ask a question. So you said, I think, actually, can you mute your mic for a moment? Okay, good.
Done.
You said that you think that when you restrict to the uniformly fibrant objects, you can get a model structure. But is that category like closed under limits and co-limits?
No, maybe not. So what I just meant was that we have two weak factorization systems. Well, there are a few classes of maps where the weak equivalences follow, such as 3 out of 2, and we get two weak factorization systems. I suspect maybe some. No, I didn't want to claim anything about limits and co-limits.
Right. Okay, maybe I'll ask a question. So you said it very quickly. So can you say again? What do you know about universes at this point, or what your hopes and dreams are?
Yeah. Okay. So what I think is clear is that we have a local notion of a uniform confibration. So if you maybe restrict, let's say, if you restrict to those uniform confibrations which have small fibers, in some sense, then this will have, then it will contain this class of sort of small uniform confiberations, will have a particular representative such that any other one is a pullback of that one. So there is at least some sort of universal uniform confibration in that sense. But of course, what we want is that so this map is just a map from E to U, say. What we also want is that U is fibrant, so that's fibrance in the universe. We haven't, I mean, that's probably the main open question. We haven't thought about that very much. And of course, we want this map to be univalent. So we want to have a univalent universe. And there, I think I'm kind of hopeful, but we haven't really done it.
Right. So I think, like in Voevodsky's model, like the fibrancy of U is the key non-constructive bit.
That's the most.
No one to talk about constructive mathematics. So hopefully someone can correct me if I'm completely wrong, but that was.
Yeah, no, it's true. That's the scariest bit. Yeah, I think that's about.
All right. Do we have any other questions? Okay, final call for questions. No one there. Okay, in that case, let's do silent applause again, and thank Benno for this great talk. And yeah, that's pretty much it for today. And we will have one more seminar this season that will be on December 11th. So in 3 weeks, not 2 weeks, but 3 weeks from now, Richard Gardner will speak, and the time is also fairly unusual. So please check your calendars. And I think that's it from me. So thanks everyone, and see you in 3 weeks.